Thank you. Thanks for the introduction. So, good afternoon, everyone. I'm Pranav Garg. I'm a scientist at Amazon Web Services. And today I'm going to talk about synthesizing code quality rules from examples. And this is joint work with Srinivasan Singamedu. Okay, so Code Guru Reviewer is an AWS service that developers can use to obtain recommendations on their code during code reviews. These recommendations belong to different categories. For instance, best practices for using AWS APIs, identifying resource leaks in your code, refactoring suggestions for removing code clones, missing input validations, security violations, and so on. And this is just a very simple example to inform you about the user interface. So a developer raises a pull request. Code Guru Reviewer generates a recommendation on the changed code. This recommendation is shown as a comment in the pull request. And in response to this recommendation, the developer could reply, or they could use this icon to upvote or downvote the recommendation and so on. So internally, Code Guru Reviewer has specialized detectors for a few for a few of these categories that I just mentioned. And besides those specialized detectors, the reviewer comprises hundreds of static checkers or rules. And each of those rules would generate recommendations for a specific category of issue. And as all of us can guess, developing these rules is not an easy task. It requires the rule author to actually learn a new DSL. And even for a person who is an expert in that DSL, creating one of these rules could take multiple days. And so our work and specifically this paper that I'm presenting, it's on facilitating rule creation, especially by synthesizing these rules automatically from code examples. Okay, so this is a pretty general problem. It's not specific to the Code Guru Reviewer. There are several static analysis software testing tools out there, including CodeQL, SemGraph, SonarQube, Coverity. All of them comprise hundreds to thousands of different rules. And so this is a general problem. It has practical implications. And I would also like to argue that programming by example is a very natural framing of the problem. So these rules are pretty complex objects, and they're best specified in terms of their behavior on code examples. And it is for this reason that when a rule creator is actually creating these rules, they first source code examples. They concretely specify what the behavior of the desired rule would be on those code examples, and only then do they start creating these rules. Okay, so just to kind of drive home this point a little bit more, and just to kind of get a better feeling of what these rules look like, let's look at a very simple example. I've not yet talked about what the rule syntax is, what the semantics is, what these rules look like, but we'll try to understand this rule through a few examples and the behavior of this rule on these examples. Right, so the rule is about checking if the result set returned by a database query is empty or not. If the result set returned by the query is empty, then any subsequent operation that tries to kind of peek into the result set would lead to a bug or would lead to a crash. Right, and here we have two examples. So the first code example is the one on red. It's a violating example. It's a buggy example. And the one in the green is a conforming or a correct example. Right, so cursor here is an object that is kind of pointing into the result set returned by the database query. The developer has a call to move to first. This is an API that one can use to move to the first position in the result set. This API returns false if the result set is empty, but the developer is not having this check here. And so the subsequent operation where they're accessing the value using getLong can lead to a crash. And in the fixed version of the code, the developer has inserted a check on the value returned by move to first. And in the case that value was false, they have an early return. Okay, so so this is so this example hopefully conveys a little bit about what these rules look like, and from this example, it's clear that that they're not like 5 rules; they're like hundreds of different rules um, dealing with kind of different APIs, different frameworks that one could conceive of, and so the problem is how can we kind of facilitate creation of these rules in an automated manner. Right, so this is we've not kind of identified, we are not the first ones to identify this problem. There are a lot of existing approaches that deal with the same, that try to solve the same problem or like a similar problem. And we could kind of cluster these approaches around these 3 main kind of ideas. So one line of work is on data log synthesis. And these approaches, they try to kind of synthesize rules, but in a slightly different fragment. So for instance, they support synthesizing rules with recursive predicates, but they do not handle negations in the fragment. We experimented with a few tools in this space early on in our project, and we found that those were relatively slow. And the key kind of differentiator is that most of these tools are based on SAT solver-based enumeration. There is no bias in the algorithm here towards like specific formulas. And so if you kind of use these tools, a lot of times they would miss the relevant code context, leading to rules that do not have a high precision. The second kind of line of work is around synthesizing rules over ASTs using anti-unification. And as you might kind of guess, these are not robust to input examples with syntactic variations and therefore have a higher sample complexity. And finally, there are approaches that are inspired by Flashfill, and these approaches rely on the richness of the output examples to backpropagate and use that to synthesize the program. And these have been very successfully applied to program repair, where the output is in the form of the fixed program. But in the case of rule synthesis, where the output is a Boolean value, true or false, these are not very appropriate. Cool. So with this kind of context, let's kind of dive into the synthesis problem in a more technical manner. So we formulate the problem as follows. We want to synthesize a rule R given a set of violating and conforming examples such that the rule would evaluate to true on the violating examples and it would evaluate to false on the conforming examples. And note that in our formulation of the problem, the violating and the conforming examples are not paired. And this is in contrast to some of the earlier works that required or that only worked on paired code changes. And so this is a more general formulation of the problem, and this allows like iterative refinement of the rule, something that I'll come to later in my talk. And we are assuming here that code examples are at a method granularity, and they're expressed using graphical representations. Specifically here, we are using the program dependence graph as a representation of the code. And again, this is something that kind of seems simple. So one, representing programs using PDGs, it makes the algorithm and our technique more robust to syntactic variations in code. But this is not a very kind of simple extension from AST to PDG, because as soon as we move from a tree structure to a graph structure, it requires a more complicated algorithm. And in a sense, you need to kind of find a new algorithm altogether. Cool. So rules in the most simplest form are existentially quantified formulas over graph representations of code, where the existential quantification is using these existential variables x, and the rule is expressing a buggy pattern over these variables x, where the buggy pattern is a conjunction over various edge and node predicates. The edge predicates are expressing relations between different nodes in the program, and node predicates are expressing properties at different nodes in the program. And so examples of edge predicates could be relations like these two nodes are like connected by a receiver edge. So the data node is a receiver of the action node, like a method call. And node predicates could be that the label at this node is a call to method foo, or the type of this node is an input stream, and so on. Okay, so if you're familiar with property graphs, which is a model that is used in graph query languages, then this is a very simple. This is a very similar model, right? Where we are basically synthesizing a graph property, where the graphs are attributed with both edge attributes and node attributes. But this is, of course, not the complete picture, because you can have a conforming example that satisfies the buggy pattern. And in this case, you need to strengthen your rule R with the negation of an existentially quantified non-buggy pattern. And the non-buggy pattern here is defined over these existential variables y, and it may share variables x that are defined, that are kind of quantified outside in the scope of the buggy pattern. And this, in fact, might also be a limitation. This might, and in fact, we need to kind of extend it further, because in general, there are multiple ways of expressing correct code, not just a single way. And therefore, we need to kind of have a disjunction here for kind of being able to capture all different ways of writing non-buggy code. And so the final syntax is as is shown in this slide. So we have an existential quantification expressing a buggy pattern, and then we are further strengthening the rule with a negation of a disjunction of several non-buggy patterns. So a few things to call out here. So one, you might note that we are disallowing disjunctions in the buggy pattern here. So this is a conscious decision. If you have a rule that involves a disjunction in the buggy pattern, you can actually synthesize the rule with each of those disjuncts separately. The second thing to call out is that the logic fragment here is really parameterized with node and edge predicates. So in the paper and in this work, we have instantiated the algorithm with a choice of around 10 predicates, and we show in our experiments that they can capture a large number of rules. But really, the algorithm is independent of the choice of these predicates. And so this allows a lot of flexibility. So if in the future we find that there are more properties that that we would need to capture some rules, we can incorporate that in the algorithm. Thirdly, each of these predicates is actually lifted to a lattice. So for instance, for expressing data types, we are lifting it to a lattice that is specifically designed over strings. Some of these predicates are over Boolean lattices. This is something like the use of this comes into the synthesis algorithm that I'll describe later. And finally, the logic fragment here is decidable. We can reduce it to Pressburger arithmetic, and the queries can be validated efficiently. Okay, so just to kind of go over the move to first example that I showed in the earlier slides. This is actually a graphical representation of the rule that was synthesized from that example and other examples for this rule. So the buggy pattern here consists of just two nodes. So the pattern, it checks for the call to move to first. And the fact that the output of this call is ignored in the code. And we are also asserting that the receiver of this call should be a cursor object. In addition to this buggy pattern, we are negating a disjunction of two non-buggy patterns. In the first non-buggy pattern, we are making sure that the code does not have a call to is after last, which is another way of making sure that the result set is empty. And in the second one, we have a call to get count, cursor.getCount, and we are kind of making sure that the program does not have that conforming pattern. Okay, so let's now look into the algorithm. So our algorithm is called RhoSynth. The algorithm decomposes this rule synthesis problem into two stages. In the first stage, we are synthesizing a buggy pattern over violating examples. And in the second stage, we find conforming examples that satisfy the synthesized buggy pattern. And we try to synthesize a non-buggy pattern over those conforming examples. And so using this decomposition, we reduce the problem to synthesizing existentially quantified conjunctive graph patterns. And this is a strictly simpler problem than synthesizing the entire rule together in a monolithic manner where the rule involves quantifier alternation. Okay, so the first stage where we're synthesizing the buggy pattern. So let's assume that these are like two violating examples. We want to synthesize a buggy pattern that satisfies both these examples, right? And in addition, we want to bias our algorithm to synthesize a more specific graph pattern, and this would ensure that the rule that we are synthesizing does not miss any relevant code context, and the rule has a higher precision. So if we knew the mapping X between nodes in these two violating examples, then one can use a fairly straightforward elimination algorithm to learn a buggy pattern over these variables X. Right, and the elimination algorithm, it's a basic algorithm for learning conjunctions of predicates. It starts with all the predicates and it eliminates any predicate that is not satisfied in the input examples. So in our case, since our edge and node predicates are lifted to lattices, the generalization would actually occur by moving up the lattice using the least upper bound. Right, so again, reiterating, if we knew the mapping X, right, so if we knew that this node in this example is X1 and this node is X1 in the other example, so if we knew this kind of a mapping, then synthesizing the buggy pattern over these variables is not very hard to see. One can use something similar to conjunctive learning for doing that. And so synthesizing these buggy patterns with the existential quantification really amounts to finding a good mapping X. Okay, so the crucial insight here is that we can actually learn this mapping X by framing the problem as integer linear program. The integer linear program looks at these examples, violating examples in a pairwise manner, and it tries to maximize graph alignment in terms of the size of the synthesized pattern. Okay, so I'll talk about the integer linear program formulation in a couple of slides, but assuming that we have this formulation which can learn a good mapping X, I think we get the idea of how we can synthesize the buggy pattern. So once we have synthesized the buggy pattern, we now want to synthesize the non-buggy patterns, right? So for that, we start with the conforming examples, and we check which of these conforming examples actually satisfy the synthesized buggy pattern, right? If none of the conforming examples satisfied the buggy pattern, then we're good, because we can just return the synthesized buggy pattern as the rule. But if some conforming examples do satisfy the buggy pattern, then we actually need to strengthen the rule by synthesizing with the negation of the non-buggy pattern. Right. So for this, we use an SMT solver. In fact, the SMT solver not only gives a yes/no answer, it also returns to us a valuation for these variables X that are used for satisfying the buggy pattern in these conforming examples. So we call such conforming examples with a valuation for these variables X as a valuated conforming example. So let's say these are two valuated conforming examples, and now the problem is, how do we synthesize a non-buggy pattern that is satisfied by these two valuated conforming examples? So the solution is pretty similar to what we just discussed. So we'll use the same procedure that is based on integer linear programming and conjunctive learning to synthesize the non-buggy pattern by finding good alignments for nodes in these valuated conforming examples, where the alignments would correspond to valuations for these existential variables y. And a small kind of caveat here. So if it's possible that we may synthesize a non-buggy pattern that is too general, in which case we would partition these conforming examples using a clustering algorithm, and we would synthesize a non-buggy pattern for each of these partitions separately. Okay, so a pointer about the graph alignment using the ILP formulation. So maximizing the graph alignment can be thought of as minimizing the graph edit distance. And there is work by LaRouche and others in 2017 that showed that finding the minimal, exact minimal graph edit distance can be formulated as ILP. Okay, so I'll just kind of at a high level go over the formulation now. Let's say these are two graphs, and we want to find an alignment between two graphs that achieves a maximal alignment. The alignment here is indicated by these purple arrows, and we can kind of numerically represent this alignment using 0-1 binary variables of these form. So we introduce a quadratic number of variables of the form zn1n2 and ze1e2 that correspond to node and edge substitutions. So the variable zn1n2 for these two nodes would be equal to 1 for this particular alignment, since these two nodes are mapped to each other. And we have a linear number of variables of the form zn1, zn2, and so on that correspond to node and edge addition and deletions. So as a concrete example, the variable zn1 for this particular node would be equal to 1 because there is no other node in the other graph that is aligned to this node. And so if you're taking the point of view of the edit distance, this node is actually being deleted when you're transforming from this particular graph to the other graph. Okay, so to maximize graph alignment is actually to maximize to find an assignments to these variables z's such that the sum over zn1n2 and ze1e2 is maximized, subject to a string of topological constraints, and these are kind of taken directly from the work from prior work by LaRouche, and also a few domain constraints. Okay, so we kind of show in a paper that our algorithm is sound, meaning that if we synthesize a rule, then it's consistent with the input violating and conforming examples. And a note about generalization. So we are biasing our synthesis algorithm towards more specific patterns, and this is a conscious decision because we want our rules to kind of not miss relevant code context so that they have high precision. And this may lead to overfitting, and in this current work, we kind of get or circumvent that outside of the algorithm by making sure that the examples that we're using for synthesizing rules are diverse. And when synthesizing non-buggy patterns, we are kind of ensuring that our algorithm is biased towards fewer disjuncts, which again kind of leads to better generalization. So this is our experimental setting. We synthesize rules from groups of code changes. These code changes are mined from GitHub Code Corpus. They are grouped together using an in-house developed clustering algorithm. The output of the clustering algorithm is subject to various automated and manual checks. Automated checks make sure that the clusters have a high quality. For instance, we want to make sure that the homogeneity score of the cluster is large. the code changes in the cluster belong to different repositories. There are at least 3 code changes within the cluster. And manual checks, we kind of look at the contents of the code changes in the cluster, and using like primitive web searches, we kind of make sure that the APIs that are involved in the code changes and the change that the cluster is talking about are generally applicable and are not specific to a particular project. And so for the clusters that kind of pass this verification step, they are kind of treated as an input to the RhoSynth algorithm. The algorithm synthesizes a rule R. We execute this rule on code corpus in an offline manner, and the result, we look at the detections that are generated by the rule, and we triage the findings. False positives that are generated by the rule are treated as conforming examples, and the rule should actually kind of reject those examples, and so those are additional examples that are input along with the initial code changes from the clustering algorithm and are used for iteratively refining the rule. And once we have obtained a rule of a sufficiently high quality, we can kind of deploy this rule in production. So we have an in-house Java-based query language for like writing these rules. And so the rule deployment proceeds by transpiling the rule into this query language. If you're interested, you can take a look at the query language, which is described in detail in the ECOOP paper from our team members. The structure of the rule is very similar to the logical formulation that I described before. Everything like before check in this query is corresponding to a buggy pattern. Everything after check is like is a disjunction of different non-buggy patterns. And the query here, it corresponds to this graphical pattern. And it kind of proceeds by asserting all the facts that are true for this graphical pattern. So I'll just go over a few like main result highlights in the talk, and for more results, you can take a look at our paper. So we use this workflow of clustering and then synthesis to synthesize and deploy more than 30 code quality rules in the Code Guru Reviewer. These rules belong to different categories, including detecting issues related to performance, concurrency, identifying usage of deprecated APIs, finding issues that would lead to bugs or crashes, and also suggestions to simplify or modernize your code. And these rules involve libraries belonging to Android, Java utils, Apache, Spring, etc. And we conducted a pretty large scale study involving thousands of developers spanning multiple months, where developers were shown recommendations generated by these rules in the code reviews, and they were able to mark those recommendations as useful or not useful. And based on developer feedback, more than 75% of the label detections were deemed useful. Right, so these are the result kind of characteristics. I'll kind of maybe skip over them. We have in the paper comparisons against baselines. You can take a look at the paper for detailed results here. So in summary, we kind of describe an expressive fragment of first-order logic, which can capture a large number of rules. We have described an algorithm for synthesizing these rules. We conducted a large-scale study, and those results from the study attest to the precision of the synthesized rules. We have detailed comparisons with prior approaches, and ongoing work. We are kind of working with developers for integrating this algorithm in their developer workflow. And we're very excited about this. We really feel that by integrating it into their workflow, we can scale the process of creating these rules. Thank you.
We have time for maybe 1 or 2 quick questions. Any questions?
From what I understood, the synthesized rules will only detect patterns of code, so they won't necessarily provide fixes for that, right?
Yeah.
Can you expand on like if there's what potential directions would allow for that kind of like synthesis of like also rewrites that would allow to update the code?
So I didn't get the question. So what was the last part of your?
So what directions do you think for this work that would allow for that ability to synthesize also rewrites or new code fragments that could update the code to be compliant?
Right. So yeah, I think that's like an independent problem, like synthesizing fixes. So the way I kind of see it, there are two problems. One is localizing bug. And then once you have localized the bug, which is what rule synthesis is doing, how do you do an automated program repair? Right. And some of the techniques can be kind of maybe transported from one to the other. But at least there is some literature. There's some literature that suggests that bug localization is a harder problem than automated program repair. And most of the work right now is focused on automated program repair as opposed to bug localization, like at a high level. So.
Maybe one last quick question.
So I understand the notion of a buggy pattern, but I don't understand what you mean by not a buggy pattern. So how does somebody say something is not a buggy pattern, and how do you sort of capture it?
Yeah, so not a buggy pattern is really in the context of a buggy pattern, right? So otherwise, like anything that is not even relevant to the rule can be considered as not a buggy pattern, right? But not a buggy pattern here is a refinement of the buggy pattern that is making your code correct, right? So it's even if the code is satisfying the buggy pattern, if it satisfies also this, then your code is really not buggy.
Thanks.
All right, let's thank the speaker.
Thank you.